Hi everyone, this is Professor M. Science, and today I want to discuss the Virial theorem in another one of our videos on rigorous quantum mechanics. The Virial theorem encodes a simple relation between the kinetic and potential energies of any quantum system. This result is immensely powerful because it holds even for quantum systems for which we don't have an exact solution. And this means it provides important insights into complex systems such as atoms, molecules, or materials. In today's video, we'll derive the Virial theorem, and then we'll look at a few examples of its application. Let's go! We start with a time-independent Hamiltonian H that obeys this eigenvalue equation. As usual, these are the eigenvalues, and these are the eigenstates. It will be useful in a moment to write this eigenvalue equation in the Joule space. Now, in general, when we go to the Joule space, we turn kets into bras, as we do here and here. We should also turn operators into their adjoints, but the Hamiltonian is a Hermitian operator, so we can write the Hamiltonian here without the adjoint. And we should also turn scalars into their complex conjugates, but the eigenvalues of a Hermitian operator are real scalars, so the energy here is real and is equal to its complex conjugate. Let's also consider a time-independent operator A. We're going to calculate the expectation value of the commutator of H and A with respect to an eigenstate of the system. We can expand the commutator using its definition, and we get this expression. To simplify things, we can now separate it into the expectation value of HA minus the expectation value of AH. Using the eigenvalue equation in the Joule space, we can now rewrite this term as the energy eigenvalue times the eigenbra. And using the eigenvalue equation in state space, we can write this term as the energy eigenvalue times the eigenket. We can take the energy eigenvalues outside the expectation value to get this term minus this term. It is now clear that this expression vanishes. We have arrived at an important relation called the Hypervirial theorem. It states that the expectation value of the commutator of the Hamiltonian with any operator A is equal to 0. And remember that the expectation value is taken with respect to an energy eigenstate of the system. Without specifying what this operator A is, we get this very general result, which as written is not that useful. What we'll do today is to use the Hypervirial theorem to derive the Virial theorem, and to do so we'll make a specific choice for this operator A. To simplify things, let's start by focusing on a single particle moving in one dimension. In this context, we can write the Hamiltonian H as equal to the usual kinetic energy operator, plus a general potential energy that depends on the position operator. To simplify notation, we'll occasionally rewrite the kinetic energy with a capital T operator and the potential energy with a capital V operator without specifying the dependence on the position operator. To make progress, we're now going to use a specific operator A equal to the product of the position and momentum operators. To use the Hypervirial theorem at the top, we'll need to evaluate this commutator. In our case, this is the commutator of H with XP. Remember from the video on commutator algebra, linked in the description, that the commutator of an operator X with the product of two operators Y and Z is equal to this first term plus this second term. Using this expression, we can rewrite our commutator as X times the commutator of H and P plus the commutator of H and X times P. Let's start with this first commutator, which we can write here. Expanding the Hamiltonian, we can rewrite the commutator as the sum of these two terms. The first term vanishes because the momentum operator commutes with any power of itself. For the second term, remember from the video on functions of operators that the commutator of any function f of the position operator with the momentum operator is equal to IH bar times the derivative of f. Using this result, we can rewrite our commutator as IH bar times the derivative of the potential. Moving to the second commutator up here, we also start by copying it down. We again expand the Hamiltonian and get these two commutators. The second commutator vanishes because x commutes with any function of x. For the first commutator, we can again use this relation up here to expand it into this prefactor, this first term, and this second term. This commutator is equal to minus IH bar, and so is this one. Overall, we end up with minus IH bar over m times the momentum operator. Let's make some room. Using the results we just got, we can write the commutator of the Hamiltonian with xp as equal to IH bar x times the derivative of the potential minus IH bar over m times the momentum squared. All we've done is literally to replace the commutators here and here with the results we got in the previous slide, but feel free to pause here to cross-check this step. Moving on, we can rearrange the expression to take IH bar out as a common factor, multiplying x times the derivative of the potential, and then I'm conveniently regrouping the term that depends on the momentum squared. This term in brackets is simply the kinetic energy operator, so we can rewrite the whole expression in this more compact form. We can now use this result for the commutator and insert it into the expression for the Hypervirial theorem. With this, we get IH bar times the expectation value of x times the derivative of the potential minus 2IH bar times the expectation value of the kinetic energy operator, all equal to 0. And we have now arrived at the Virial theorem. The expectation value of x times the derivative of the potential is equal to 2 times the expectation value of the kinetic energy. It is very important to remember that the Virial theorem only applies when the expectation value is evaluated with respect to an energy eigenstate. And this is why so far I've written all expectation values with the explicit eigenstates, for example here and here. However, moving forward we'll simplify notation and write expectation values in the usual shorthand, which means that the Virial theorem becomes this. We'll just have to remember that we're calculating these expectation values with respect to the energy eigenstates of the system. Let's now try to understand a bit more what the Virial theorem means. It provides a very general relationship between the expectation values of potential and kinetic energies without the need to explicitly evaluate them. Evaluating expectation values can be tedious. For example, it may require long integrals if we work in the position representation in terms of wave functions. On top of that, most quantum systems cannot be solved analytically, which means that we often have to work with approximate solutions. In all these cases, the Virial theorem becomes a very powerful and useful result. It provides an exact relation that can help us explore some properties of the system even if we don't have a full solution. Or it can also help us understand the quality of any approximate solutions we may have. Interestingly, there is also a Virial theorem in classical mechanics. The result is analogous to the one we just obtained in quantum mechanics. 2 times the time average of the kinetic energy is equal to the time average of x times the derivative of the potential. Now I'm using the same symbol of angle brackets, but the meaning in classical mechanics is that of a time average. In classical mechanics, we know that the force acting on a system is equal to the negative gradient of the potential. So we can also rewrite the classical Virial theorem using the negative time average of x times the force. And this is actually where the name Virial in Virial theorem comes from, specifically from the Latin word vis, which means force. The Virial theorem takes a rather simpler form for a special class of potentials, and this is what we'll investigate next. Specifically, we're going to consider potentials that are described by a special type of function called a homogeneous function of degree k. By definition, a homogeneous function f of degree k is one for which f of sx is equal to s to the power k times f of x, and where s is a non-zero scalar. As an example of a homogeneous function, we can consider a quadratic function, where lambda is simply a scalar coefficient. In this case, we can explicitly confirm that f of sx is equal to this, which we can rewrite as s squared times lambda x squared, which in turn is equal to s squared times f of x. Given that we have a power of 2 here, we can conclude that the quadratic function is a homogeneous function of degree 2. We also need an important result associated with homogeneous functions called Euler's theorem. It states that for a continuously differentiable homogeneous function of degree k, then k times f of x is equal to x times the derivative of f. The proof of this result is very simple. Starting with the definition of a homogeneous function of degree k here, for the proof we need to calculate the derivative with respect to s. Let's first evaluate the derivative of the left-hand side. Using the chain rule, we get the derivative of f with respect to sx times the derivative of sx with respect to s. This here is simply x, so we can rewrite this derivative as x times the derivative of f with respect to sx. For the right-hand side, we get the derivative of this expression, which is simply the derivative of the power times f of x. Equating these two sides, we get this expression involving the derivative of f as equal to this other expression involving f. Finally, setting s equal to 1 gives us Euler's theorem up here. All of these ideas can be easily generalized to multivariable functions, and will explicitly show the corresponding results later on in the video. We are now ready to rewrite the Virial theorem for potentials that correspond to homogeneous functions. If the potential V is described by a homogeneous function of degree k, then by definition it obeys this relation. Using Euler's theorem, we can then conclude that k times the potential is equal to x times the derivative of the potential. We can now insert this result inside the Virial theorem up here, and this takes us to the Virial theorem for potentials described by homogeneous functions of degree k. We have that k times the expectation value of the potential energy is equal to 2 times the expectation value of the kinetic energy. As promised, this new expression provides a simpler form for the Virial theorem in the special case when the potential is described by a homogeneous function. Now, this expression for the Virial theorem can be rewritten in a few alternative forms. Remember that the Virial theorem applies when we take the expectation value with respect to an energy eigenstate. If we consider the expectation value of the Hamiltonian, and I will explicitly write it out with respect to eigenstate n, then it is simply equal to the eigenvalue En. Note that as the Hamiltonian is the sum of kinetic and potential energies, we can also rewrite this as the sum of the expectation value of the kinetic energy and the expectation value of the potential energy. We now have two equations relating the expectation values of the kinetic and potential energies. The first one is the Virial theorem up here, and the second is this one here, that describes the fact that the total energy of the system is equal to the sum of the kinetic and potential energies. From these two equations, we can isolate the expectation value of either kinetic or potential energies. I'll leave it as an exercise for you, but it should be easy to confirm that we get the expectation value of the kinetic energy as equal to k En over k plus 2, and we get the expectation value of the potential energy as equal to 2 En over k plus 2. Now, while these results are rather neat, you may be wondering how relevant they are, as they only apply when the potential is described by a homogeneous function. Well, as we'll see in a moment, there are plenty of very important potentials that are described by homogeneous functions. To consider an example of the Virial theorem for a potential described by a homogeneous function, let's consider the quantum harmonic oscillator. Remember that in this case, the Hamiltonian H is equal to the usual kinetic energy, plus the potential energy which depends quadratically on the position operator. We've already discussed earlier that the quadratic function is a homogeneous function of degree 2, and you can easily confirm that this is the case for the potential of the quantum harmonic oscillator. Using the Virial theorem, we can then immediately conclude that for the quantum harmonic oscillator, in any energy eigenstate, the expectation value of the potential energy is equal to the expectation value of the kinetic energy. And this is an example of the power of the Virial theorem. we can reach this result without having to solve the quantum harmonic oscillator problem. All we need to know is the form of the potential. In the case of the quantum harmonic oscillator, we do actually know how to solve the problem, and I encourage you to confirm this result explicitly. However, as we discussed earlier, there are many quantum problems for which we don't have an analytical solution, but the Virial theorem still applies in those cases. Even though our discussion so far has been limited to a single particle moving in 1D, we have in fact already covered all the important aspects of the Virial theorem. Moving to 3D and moving to multi-particle systems is a simple generalization of this discussion, and to finish the video I'll quickly describe some of the key results and you can fill in the gaps yourself. We consider a system with n particles, whose positions are described by the vector operator r, which is given by the three components x, y, and z. These particles are also characterized by their momentum operator p, with components px, py, and pz. The subindices I here and here label the different particles, and I runs from 1 to n. For this system, we can write the Hamiltonian h as equal to the sum of the kinetic energy operators for each particle, plus the potential energy, which in general depend on the positions of all particles. Again, we'll conveniently label this term as the kinetic energy T, and this term as the potential energy V. Following the same strategy we used for a single particle moving in 1D, we can write the Virial theorem as the expectation value of this sum over the product of the position operator and the gradient of the potential being equal to 2 times the expectation value of the kinetic energy operator. Just like in the single particle 1D case, many important potentials have the form of a homogeneous function, and this expression for the Virial theorem can be simplified further in those cases. And this is what we'll explore next. Very briefly, we can generalize the definition of a homogeneous function of degree k to functions of multiple variables. The definition is that when we scale every single one of the variables by the same scalar s, and here we consider a function f of n variables, then we get s to the power k times the original function. And remember that s is a non-zero scalar. We can also generalize Euler's theorem. The derivation is completely analogous to the one we provided for the single variable case, and Euler's theorem states that k times f is equal to the sum of x times the derivative of f with respect to x. With the results we've just discussed, and using the same argument we used for one particle in 1D, we can now consider the Virial theorem for a multi-particle system described by a potential that is a homogeneous function of degree k. We have that k times the expectation value of the potential energy operator is equal to 2 times the expectation value of the kinetic energy operator. Let's consider two quick examples. The first is for the hydrogen atom, which is a two-particle system in 3D. We have a full series on the hydrogen atom, and I recommend you check it out by following the relevant links in the description. But what matters for our purposes today is that the potential energy of the hydrogen atom is given by the electrostatic interaction between a proton and an electron, and it takes its usual form. Note that here we're considering a non-relativistic hydrogen atom. Spelling this out, we see that the potential energy is a function of 6 variables, and explicitly we can write it out in this long form. Feel free to pause here to cross-check this, but all we've done is to spell out the distance between the proton and the electron in the denominator. Moving on, with this expression, it's easy to confirm that the potential function obeys this relation when we multiply the arguments by a scalar s. The exponent here means that this is a homogeneous function of degree -1. Now, we haven't done this explicitly, but it's a good exercise, so feel free to try it out. But now we come to the key point. Without the need to find the hydrogen atom eigenvalues or eigenstates, we can immediately use the Virial theorem to write that for any energy eigenstate, the expectation value of the potential energy is equal to -2 times the expectation value of the kinetic energy. Now, the hydrogen atom, together with the harmonic oscillator, is one of the very few quantum mechanical systems for which we have a full analytical solution. In fact, in the video linked in the description on the ground state of the hydrogen atom, we explicitly calculate these expectation values and confirm the Virial theorem. However, to get to this result using the full solution is a rather tedious process, as solving the hydrogen atom eigenvalue problem isn't trivial. By contrast, using the Virial theorem, we can get to this same conclusion without any knowledge of the precise form of the hydrogen atom eigenvalues or eigenfunctions. Let's make some room and consider a second example, which will be a very general quantum system, an atom, a molecule, or a material. All these systems are made of a single atom or of a collection of atoms. In turn, these atoms are made of a collection of atomic nuclei and electrons. However, irrespective of how complex the system is or of how many particles it has, the potential energy terms always have the same form. Ignoring relativistic effects again, the component particles all interact via the electrostatic interaction, and the interaction V between any two particles 1 and 2 takes the same general form. We have the usual prefactor, and then the product of the electric charges over the distance between the two particles. As this form is the same we had earlier between the interacting proton and electron in a hydrogen atom, we can immediately conclude that these two-body interaction terms obey this relation and are therefore homogeneous functions of degree -1. The total potential energy of a multiparticle system is the sum of the individual two-body terms, so the total potential energy is also a homogeneous function of degree -1. We can therefore use the Virial theorem to conclude that for any eigenstate of any of these systems, the expectation value of the potential energy is equal to -2 times the expectation value of the kinetic energy. This is a very general result, and again, we have been able to obtain it without having to first solve the eigenvalue equation of the Hamiltonian to determine the eigenvalues or eigenstates. Unlike hydrogen, for any of these systems, it is impossible to exactly calculate the energy eigenvalues or eigenstates. The Virial theorem then tells us that whatever form the unknown solution of the problem takes, it must obey this relation. The Virial theorem is a very neat mathematical result that allows us to understand some key properties of any quantum system, even if we don't have a full mathematical solution. As a follow-up, I recommend that you check out the video on the ground state of the hydrogen atom. In that video, we can demonstrate analytically that the Virial theorem is satisfied. And as always, if you like the video, please subscribe.